much, Szymon. I would like you to stay longer with us because you have the second presentation titled Identification of Objects on Satellite Images with the Use of Deep Machine Learning. Welcome, the floor is yours. Again, good afternoon. I would like to continue my considerations regarding integration of BIM and GIS data, especially from the perspective of geographic information from GIS perspective. And precisely, I would like to tell you something about raster data and extraction of this type of information for infrastructural needs with the use of deep machine learning or deep neuronic networks. I would like to start the presentation from discussing what raster data are. Raster, most simply speaking, is a matrix in cells of which, named pixels, information of value of some phenomenon is recorded. So, example, schematic record about raster has been presented on the left-hand side of the slide. In the pixel, not necessarily we have to have RGB space, but it can be height of points in grid. So numerical model of terrain can be presented as a raster in scale of gray. We can see that this record can be multidimensional, but we can also record information about many channels and then merge them, obtaining information which are not visible with open eye. Well, on the right-hand side, we can see information created by pixel by allocating class and then a reference to RGB. RGB, three basic channels of spectrum of colored light and in real colors, but we do not need to stay with 3 channels. We can use 13 channels as it is in Mission Sentinel. Now I would like to present and classify raster data because of the source of their obtaining. But I would like to show you the possibility to obtain the data from some level above ground. First source is unmanned vehicles, drones, which we have heard a lot about, and we will hear quite a lot about during this conference. So I would like to very briefly describe the features of data obtained, raster data obtained from drones. In most cases, they cover a small area, but they have a small terrain pixel, low cost of obtaining them, and when taking measurements, most often it is possible to supply additional products like crowd of points or orthomap plane, just like drones, but it is already able to cover much larger an area, often with a bit larger terrain pixel. It results from the height of taking the pictures. Cost of obtaining is much higher, but just like in unmanned flying objects, we have the possibility to obtain additional products like point cloud. I would like to focus here on satellites. They cover a very large area and medium size and large pixel of the terrain, depending on whether the data is commercial or free of charge, and cost of obtaining depends on this. So it can be medium, low, or high cost, depending on size of terrain pixel which is chosen. But in most cases, we have the possibility of multispectral analysis thanks to this, because imaging in multi-channels allows us to image what is not visible with naked eye. So analyzing various indicators, we can analyze things related to plant cover, more for environmental things. Like for infrastructure, we have the possibility to read various kinds of information too. Raster data can be characterized by 3 main features. Firstly, it is spectral resolution, so how many channels are being registered. Then optic sensors placed on drones. These are in most cases 3 channels, RGB, but satellites in most cases register larger number of channels. So Sentinel can register in 13 channels, and as I had mentioned, by application of various types of analysis, it is possible to read what normally is not visible by a naked eye with the use of standardized features and time resolution. That means how often imaging is done. For a drone or plane, it results from contracts which are signed with a subcontractor, whereas satellites all depends on specification there. So, for example, Sentinel, a time of revisit over the same point on Earth is 5 days. Of course, we have to keep in mind that it is also dependent on atmospheric conditions, because not always such imaging is possible to be done. If the atmospheric conditions are poor, it can be impossible. And now, geometrical resolution, what is the terrain pixel size? I would like to tell you that in the next slide. Geometrical resolution is defined by size of the terrain pixel. So actually it means how much information we are able to read from the given value of the terrain pixel. I would like to present you now, based on example, how it can be happening. As a base source, orthophoto map was used where we should be, if not for pandemia. It means around the hole in Gliwice. Geopixel for the portal is 4 centimeters, very great accuracy as for free sources. Comparing 4 centimeters to 10 centimeters, we are not losing so very much information. We can read number of stairs present in the slide. With a 25 centimeter pixel, it would be a problem. We can be guessing that it is stairs, but it can be a ramp. But with 1 meter pixel, well, we can identify objects. Then 3 meters identification is possible, but we will not get detailed information. 10 meter pixel allows us to identify only the largest objects, and 30 meters pixel is used only for macro scale, for environmental analysis, because it contains information about many other channels. So we should consider what information is necessary to obtain data, raster data, and to apply appropriate size of terrain pixel. Another element I would like to introduce into deep machine learning in case of analysis of extraction of information, we should consider convolution networks. Most simply saying, it is a model which through various analysis and operations allows for the range. It automatically identifies typical features for the given class for entry data. This process can be going on various levels of depth, so it can be using many convolutions, and as a result we obtain information about, for example, allocation to the given class with using softmark function, and we can determine the degree of probability of allocation. Similar activities can be done in the segmentation of the image, which I would like to present now. However, in order to start working with convolution network, we have to have some data set which will be a basis for training. So if we want to talk about extraction of information, we must have some learning set. Creating it, for example, may be done by creating maps or vectorization or labeling of the resources. This slide presents possibilities of ARGIT. In this case, example of segmentation and classification of image may look like this. In this slide, you can see the outcome of a unit network working on based on convolution networks, and raster data was starting data, and after going through, we can see an image with allocation to individual classes, which had been defined on the entry to the network. It allows to extract really detailed information. For example, having an appropriate learning set, it would be possible to classify a 4 centimeter pixel image, the one which you can obtain free of charge from GeoPortal, thanks to which it is possible to obtain information of really high accuracy. Actually, with accuracy of up to 4 centimeters. Well, actually, application for using convolution network for detection of changes. So we actually download some images from 2 time series, then extraction of features takes place by application of convolution network, and then calculation of differences and generation of final effect of changes. So we can see what has changed between these 2 time series. And for example, we can use this type of activity in infrastructure at the implementation phase for evaluation of how progress was going on in construction work. Last example of application of raster data alone without machine learning is the possibility to trace progress of work. Here in the attached picture you can see a portion of construction of Zakopianka Road at the northern entrance to the tunnel, where we managed to obtain imaging for pixel of about 3 meters size, and you can see how individual work was done starting 2016 until 2020. Thank you very much for your kind attention. Thank you very much, Szymon, and thanks to the whole team from AGH University of Technology.